again. Welcome back to the chemical process course. So we are going to again go back to our quick review of what we discussed in our last class, right? So I believe most of the time we spent looking at phase equilibrium, and the different phases, I guess what now, liquid, gaseous and solid phases. So we looked at some of the models that give us an idea of partitioning of a compound between liquid and gas. I believe we looked at Henry's law and Rod's law. Henry's law in the dilute systems, Rod's law in non-dilute systems, right? And then we looked at liquid partitioning, and a widely used variable is the octanol water partitioning coefficient. That is something that we looked at. And then fluid and solid. Fluid is either a liquid or a gas, right? We looked at various models for this partitioning. I believe we looked at linear, Freundlich and Langmuir models, right? And then we also looked at one particular example of phase equilibrium, So we have two phases, or had two phases, one is water and one is gas. So we had initially all the compound only in the water, and after equilibrium or phase equilibrium, we wanted to calculate what is the concentration at equilibrium in both the phases, right? A particular compound was initially only in liquid phase and later on in both the gaseous and the aqueous or water phases, right? So we looked at two aspects there. We looked at material balance or mass balance, and then because it is a phase equilibrium, right, we looked at the relevant equilibrium equation, right? And what was that? I guess that is going to be, we looked at the Henry's law, right, which gave us the relationship between concentration in the gaseous phase to the concentration in the water, concentration of the relevant compound in gaseous phase to the concentration of the relevant compound in water at equilibrium. So once we had these, we had two equations for two unknowns, and we could go ahead and solve the system, and this was with respect to the phase equilibrium, and the example 2 was relevant to phase equilibrium. And so then we moved on to chemical equilibrium, right, and we looked at a particular example of acetic acid, and I believe I am using HAAC as representing acetic acid. So it can dissociate into H plus and AC minus, right, similar to, not similar I guess. So how do we calculate the pH or the relevant concentration of the deprotonated acid, deprotonated base and protonated acid, right? Protonated form and deprotonated, I guess it is self-explanatory. Right, and we looked at a particular simple model where we try to have a new term called total acid would be equal to HAC and AC minus, and we know total acid was what we put in initially, HAC naught, and we could calculate that and move ahead with our solution now, right. But the issue was, if we have any other compounds like calcium or any such metals, let us say, that can complex with your acetate, then this equation is going to be invalid, or this particular total acid equation is going to be invalid, and we were not sure about how to go forward, right. So for that we are looking at a generic approach, and that is going to be a component balance. So this is something we will be discussing throughout the class, a component balance. So we are going to introduce a new concept here. So we are going to define components here, and they are nothing but chemical building blocks. So I will try to make it easier to explain in the next slide, but I need to give you some background. So for example, I guess in this particular case, let us say if it is HAC, H plus and AC minus are the three species, and again another term species, compounds present at equilibrium, equilibrium, I guess. So, species are those compounds that are going to be present at equilibrium in your particular solution, right. So, then I will need to choose or define something called components, which I will call our chemical building blocks, right. Building blocks. Why do I call them building blocks? I mean, people might have certainly played with these at home, I guess, when they were a child. So, you have building blocks, you can use them to build different structures, right. You can dismantle them and again put them together to get different shapes, right. So, again I think the concept is relatively similar, and that is what I am trying to get towards I guess. We will come back to this. So, for example, here my system is that initially I am putting in acetic acid in my solution, and I want to know the concentration of these three species here. And species, what are they? They are the compounds that are present at equilibrium in your solution, right. So, for this, for generic approach which is applicable every time, I need to be able to define components. So, before we go further, let us look at the next slide that I have here. So, here let us say I have three compounds, I guess. Call this compound 1, compound 2 and compound 3. So, I guess to make you understand, I am using the analogy with respect to building blocks, let us say, right. So, here you can replace these three compounds by HAC, AC minus and H plus, or any other examples that you can think of, let us say, right. So, if you look at this particular system, not system, pardon me, the compound, it has how many building blocks? I guess three building blocks, A, B and C, right. And compound 2, I guess, that has 2 building blocks, B and C, and compound number 3 has again 3 building blocks, I mean 3 different kinds of building blocks. There are 4 building blocks here, but 3 different kinds of building blocks in C1, 2 different kinds of building blocks in C2 and 3 different kinds of building blocks in C3. So, what we are trying to look at is, I am calling A, right, the building block A total, how many is that equal to? That is equal to 1, 2 and 3. So, that is what I have here, and what we are trying to look at here is that the total number of or total component is going to be conserved. So, that is called the component balance, right. And same case here now, here again we have B total, and that is equal to 4. How we look at that? One building block here, second, third and fourth. So, the total building blocks with respect to B or B total is equal to 4 here, I guess, right. And again same case with respect to C total, here it is 1, 2 and 3, yes. The C total again here, this is what we have here. So, what we are trying to get at is, let us say I can use A and B, I guess I am using the same colored pen so that I am going to get done faster, so please excuse me. So, this can be a compound 4, or B and B can be a compound 5, right, and then the A total can change depending on the system. But for one particular system, the A total or B total and C total will always be constant, and the rearrangement of these building blocks A and B within each particular compound can change them. So, again we are developing a concept of a component balance. So, I will try to make that clearer hopefully in the next slide, I guess, right. So, let us look at one example here and take you through the relevant steps involved here. So, we will consider a relevant or a simple example here. A plus B is going to form C, or A and B are what we say reacting with each other and forming C, and so this let us say is a reversible, or this system can be at equilibrium. So, in general in this component balance approach, this is a component balance approach which is applicable everywhere or in all the situations. Right, to calculate, what do we use this for? To calculate concentrations of compounds at equilibrium, right. A minor change to my example is going to be that instead of C, obviously to make you understand, I am going to call that as AB, right. So, compound A reacts with compound B to form a new compound called AB, and this will be at equilibrium, let us say, or these can be at equilibrium. So, what do we need to first define? I guess we need to define our components which are conservative quantities. So obviously I guess I am calling this first step, but we will see why there will be an issue here. To be able to define components, I first need to know what is going to be present in my solution, right. What does that mean? So at equilibrium, what are the different species present? So first I need to be able to list the species, not the components. So first I will identify all the species present at equilibrium. So what does that mean? In this case it is A, B and AB, right. The first step would be identifying the species. So once I identify the species, I will then choose components, right, the minimum number of components to be able to form all my species. So when I say form though, it is not a chemical reaction, it can be any hypothetical equation too. So here what do I need to, or what are the components in this case? I can choose A and B, right, or I can choose AB and B, or I can choose AB and A. But in general the most simplest form will be the simpler building blocks. So we can choose A and B as my building blocks, right. So all the three forms are component forms are feasible, but in general for calculations and getting the relevant constants later on, it is easier to choose the simpler building blocks, which in this case are going to be A and B, right. And then the next step would be writing the formation equations. And one aspect here that I need to clarify is that the components, right, the components, they can be hypothetical blocks, they do not need to be something that you would see in nature or such, but in general it makes they can be hypothetical, but species are what you would actually observe or expect to see at equilibrium in your solution, right. So formation, I guess, so formation as in we are trying to form all the species A, B and AB. So how can I form them? This is not a chemical reaction, keep in mind. So I need one block of A to form one compound A. I need one block of building component B to be able to form one block of B, and similarly I need one block of A and one block of B to be able to form the compound AB. And the choice of the components in this case was components A and component B, right. We are not looking at these particular combinations though. Yes. So this is what we have the formation equations. Keep in mind that these are not chemical equations now, right. So again let us moving on, then we need to I will just write this up here. So then we are going to have to list a tableau, right. So there we are going to have different components and the columns, the rows are going to be species. So components in this case were A and B, and the species in this case were A, B and AB, and then I am going to look at the relevant contribution. So I need one component of A to be able to form the species A, right, and 0 here and 1 here. And again B, I need 0 of B to form A, I need 1 of B to form B, and I need 1 of B to be able to form AB here, right. Again let us look at that. These obviously are from your formation equations now, right. The first formation equation, how many A do I need to form A? Obviously 1, that is what I have here. And how many A do I need to form B? 0. And how many A do I need to form B? I have 1. Same case with respect to B, right. And in the end I guess we need to have the recipe species or the initial species that were added. So as you know, let us say, okay, we will come back to this with respect to the state example, but for example initially we added AB naught, let us say, right, to your solution. You will say that is your recipe species, so that is going to be 1 1 here, I guess, yes. And then the component balance equation, right, A total is equal to concentration of A, which is this here, 1 times concentration of A plus 0 times concentration of B plus 1 times concentration of AB, right. That is what you see here. I am just balancing out this particular component. Similarly, I can balance out the component B, and B total is going to be 0 times concentration of A plus 1 times concentration of B plus 1 times concentration of AB, right. And as you can see here, what is the source of all A or all B here? It is only coming from the initial compound AB naught that you are adding, or AB naught initial concentration. And so this is a generic approach that can always be used. And what are these equations here? I guess these are the component balance equations, right. These are the component balance equations. So in general, you obviously won't have enough equations with just your component balance equations. Then you will look at your equilibrium equations to solve the system. So this is a generic approach here, right. So we are going to look at a more specific example now. So let us say I am initially adding H2SO4 of a known concentration, right, and I want to know the final pH of that particular solution. So first, what do we do here? We need to what do we say, list the species. Again, the example is that we are initially adding H2SO4 to my system, and I want to calculate the pH of this system, let us say, right. How do I calculate the pH? And this particular term obviously, or nomenclature means that is the initial concentration that I am adding here. So what is our approach here? Species are to be listed, and we know the relevant equations from acid base, which we will cover again later, I guess. H2SO4 is in equilibrium with H plus and HSO4 minus, and HSO4 minus can further dissociate into H plus and SO4 2 minus, right. These are the two equilibrium two equations that we are considering for now, or if when we have only H2SO4, these are the only equations that we need to consider, other than obviously H plus or H2O dissociating into H plus and OH minus. So this particular what we say nomenclature means it is at equilibrium, or it is a reversible reaction, right. So what are the species here? Species are those compounds that will be present at equilibrium, right. So in this case, what are they? So they are H2SO4 and they are HSO4 and HSO4 minus and SO4 2 minus, and obviously H plus, whenever we have H plus, obviously OH minus, and in general there is always water, because these are all aqueous solutions. But we can get by without listing water as your species, because we assume that these are dilute systems and that the activity of water is more or less a constant, right. So that is why we usually do not need to list the H2O or water as a species. So now I need to choose my components, and how do I do that, I guess. So I want to choose these building blocks, either hypothetical or real, right, so that I will be able to form as in even mathematically, I guess you can think of that, form all my species, right. There are different combinations, but the most easiest way would always be to choose H plus as one of your components, right, and then look at the most deprotonated form of your acid base system, which would then be SO4 2 minus. So you can use any other what do we say combinations, but in general thumb rule is that to use H plus and also to use the most deprotonated form of your acid base system, right. So these are my components, and the next aspect is writing the formation equations, right, formation equations. And first I will list all my what is this now species here, because I am trying to form my species, right, and let us look at how I can form them. So obviously I need 2 blocks of H plus and 1 block of SO4 2 minus. So keep in mind that this need not be similar to any chemical reaction that you see, this as in these formation equations can be hypothetical, I guess, right. And then we need 1 H plus and 1 SO4 2 minus, to be able to form your HSO4 minus. I only need one SO4 2 minus to form SO4 2 minus. I need one H plus to form H plus, and then people are usually stuck with how do I get to OH minus. But if you keep in mind, H2O is always again a component, so H2O or minus H plus will be equal to OH minus, right. So with this, as you see, I was able to form all the 5 species that I wanted to: H2SO4, HSO4 minus, SO4 2 minus, H plus and OH minus. So here we are going to go to the Tableau, right. Once you are proficient, you can skip the formation equations and directly go to the Tableau, right. And what are we going to have here? We are going to list the 2 components, and what are they? H plus and SO4 2 minus, and then list the species. They are H2SO4, HSO4 minus, SO4 2 minus, H plus and OH minus, right. And then we are going to have the recipe species, which we are going to talk about later. So now I want to look at H plus, and how many H plus do we have in H2SO4, and that is in this equation. We need two components of H plus, and how many do we need to form HSO4 minus? We need 1, and we need no H plus to form SO4 2 minus, 1 to form H plus, and none to form, or not 1, pardon me, it is going to be minus 1, so minus 1. So they are all relevant to these formation equations here, right. So same case here as with respect to SO4 2 minus. So how many SO4 2 minus do we require to form H2SO4 here, and that is from this initial formation equation. So you need 1, again same case here, 1, 1, 0 and 0 2, yes. And so as we talked about, once we list the species, we need to also look at the recipe species or whatever it is that you are adding initially. And what is that here? I guess you are adding H2SO4 initially, right. And again we need to write the relevant component balance there. So you need 2 components of H plus and 1 component of SO4 2 minus, right. So I will continue the workout here. And so the total component balance for H plus or H total, so H total is equal to 2 times the concentration of H2SO4 plus 1 times the concentration of HSO4 minus plus 1 time the concentration of H plus minus or plus 1 into minus 1 times concentration of OH minus, right. And this is nothing but from the component balance equation here, or from the table, and that obviously, as we know, is equal to 2 times, and where is this all this coming from? From the initial solution that you added, H2SO4 naught, right. And this is what we see here. And same case with respect to SO4 total, and that is the balance of this particular system or column here. SO4 total is equal to 1 times H2SO4 plus 1 times HSO4 minus, right, plus 1 times SO4 2 minus. And what is this all coming to, or what is the only source of SO4 2 minus in the solution? It is the H2SO4 we added initially, and so again 1 times H2SO4 naught. So usually what is your unknown here I guess, not unknown, pardon me, the known H2SO4 or whatever it is that you are inputting initially, this is your known value, right. And here we are trying to calculate the pH. Yes, what is the pH of the solution? So if you can just solve this one equation, I guess, right, H total, we will be done. So let us see, or let me move on to the next page and how to solve that. So we had H total is equal to 2 times concentration of H2SO4 plus 1 times concentration of HSO4 minus plus I believe H plus minus OH minus. All these are concentration, and that we know is equal to a constant call of H2SO4 that we added initially, the recipe species 2 times I guess. Let us see if we made any error here. 2 times 1, 1 minus 1 and 2, yes, that is right here, right. So here we are trying to solve this equation to be able to calculate H plus I guess, right. And so for this, obviously again we have SO4 total again. So you have that equation, but that just by 2 equations you can't solve for how many unknowns. How many unknowns do we have here? We have 5 species, I guess, 1, 2, 3, 4 and 5. So we have 5 unknowns, right, which are, what are they now? H plus, OH minus, SO4 2 minus, HSO4 minus and H2SO4, right. But we have only 2 equations from the component balance. So how many component balance will we equations will we have? The number of components we have, I guess. So we have 2 component balance equations. So we need 3 more equations, independent equations. So where are we getting those 3 equations from? We know that the system is at equilibrium. So thus we can get the relevant equilibrium constants for the 3 reactions that were involved. What were the 3 reactions involved? H2SO4 can dissociate into H plus and HSO4 minus. HSO4 minus can dissociate into H plus and SO4 2 minus, and water can dissociate into H plus and OH minus. So now we will have what do we say, 3 equilibrium equations. I will call this Ka1, we will explain what that is later. And what is this equilibrium coefficient equal to? Activity of H plus into activity of HSO4 minus by activity of H2SO4, and Ka2 will be equal to activity of H plus, activity of SO4 2 minus by activity of HSO4 minus. And the final water dissociation, I guess, is going to be activity of H plus by activity of OH minus, and activity of H2O is equal to 1 here, liquid, and here I guess it is activity of H2O, right. And as you know, activity of a liquid, if it is a pure liquid, is again mole fraction equal to 1, so we do not need to list the denominator here. So now how many equations do we have? We have 3 additional equations, 1, 2 and 3. And we have 2 component balance equations. So for the 5 unknowns, we have 5 equations, and we can solve them using Excel or MATLAB, right, and then get the solution, I guess, right. So I guess with that we will wrap up for today and look at a few more what do we say, examples probably in the next class before we move on to kinetics. Thank you.